Alright, we are back for part 2 of the video for 5-2 notes. We have 3 problems here that we are going to find the local extrema and the intervals where it's increasing and decreasing. I have great help here, maybe you do too. Looking at the first one, so if we're going to find the local extreme values, we need to find where our derivative equals 0 or is undefined. So the first thing I have to do is find my derivative. F prime at x equals 5 minus 2x. Quiet, girls. I set that equal to 0 because it's never undefined. Negative 2x equals negative 5 divided by negative 2. X equals 2.5. So that's where my local extreme value is going to happen, and I'm not sure yet if it's going to be a maximum or a minimum. In order to find that, let's go ahead and find the increasing decreasing, because then we'll know whether it's a maximum or whether it's minimum depending on whether it's increasing first or decreasing first. So in order to find where it's increasing, I'm going to take that derivative, 5 minus 2x, and set it greater than 0. So negative 2x is greater than negative 5. Divide by a negative 2. Think back to algebra. Algebra 1, when you divide by a negative, you switch the sign. So is less than 2.5. So this function is increasing when x is less than 2.5. So we can answer that part of the question. Don't touch. Increasing from negative infinity to 2.5. Alright, so now I need to find where it is decreasing. So I'm going to do that same thing, but set it, don't touch that, 2x less than 0. So we have negative 2x is less than negative 5, and x is less than 2. Wait, I divided by a negative, so we need to switch the sign. X is greater than 2.5. That's where my function is decreasing. So we'll write the word decreasing. And from 2.5 to infinity. I'm not sure if you caught it, but I just caught it. When we're increasing, decreasing, we're supposed to have closed intervals. So let's change that parenthesis to a bracket there on my 2.5. Okay? Yeah, it's right. Okay, so now trying to decide whether this number right here is going to be a local max or a local min. It is increasing first, and then it is decreasing. So this point, 2.5, is where a maximum occurs. That's where the maximum occurs. To actually find the maximum value, you would put that x value into this original and find the y value. And I'm not going to do that right now, but you guys should be able to find that y value by putting x into your equation. Alright, moving on to the second one, starting by finding my derivative. I'm thinking of this as x to the negative 2. And so I have negative 2x to the negative 3. This function, which is negative 2 over x cubed, is never going to be 0, and it's going to be undefined when x equals 0. So it has a critical point at x equals 0. Well, that's my initial thought, is the critical point is at x equals 0. But then you look at the original function and you notice that 0 is not in the domain of my original function. So actually we have no critical points here, so there's no maximums or minimums. Okay? Alright, so that takes care of that first part. We still have to figure out where my function is increasing and decreasing. So, hey buddy, what do you want to do?
Pooh!
Hey, don't sit in that desk, Sophia.
Why?
Because I don't want the iPad to fall. Alright, so I take my derivative, negative 2 over x cubed. Hey, stop. And I look at where it is positive. Well, if it's going to be positive, I need to take a negative number divided by a negative number. And x cubed is negative when x is negative. So this is going to be increasing when x is a negative number. So when x is less than 0, from negative infinity to 0, this is increasing. Okay. Now I need to figure out where it's decreasing. So my negative 2 over x cubed is less than 0. That's going to be negative. I have a negative divided by a Positive will make it negative. So when it is positive, so it's decreasing when x is bigger than 0. So, change it to a bracket again. So from 0 to infinity, it is decreasing. So no max and min, increasing from negative infinity to 0, decreasing from 0 to infinity. And if you just take a second and remember what that graph looks like, that would make sense to us. No maxes, it's increasing there, it's decreasing there. One left to do, maybe I'll let you guys do this one on your own. Find out where it's increasing, where it's decreasing, and where the local max are. Of those three, local max, local min, increasing or decreasing, there's only one that actually has an answer. Alright. So, not done yet. Let's keep going. We need to think about what it means for my derivative to be equal to 0. So it says that if f at x equals 0 at each point on the interval I, then there is a constant c for which f at x equals c. So if your derivative is 0 the whole time, then it's saying you must have a horizontal line. Okay?
Mom.
Another thing about antiderivative, or excuse me, I won't use that word yet, about my, what honey? Yes, go sit against the wall. Alright, so another thing about our derivative function is that every time I'm taking the derivative of a constant, it goes to 0. So these two graphs, which are just different by a +1, have the same exact derivative. Interesting enough then that there are an infinite amount of graphs that are going to have the same derivative. So what does that mean for us? Well, if we are working backwards, so not taking the derivative, but working backwards, we call that the antiderivative. So if we are trying to find the antiderivative, then we need to know that, that there's going to be an infinite amount of functions that will give us that. So let me quickly just define this. A function capital F at x is an antiderivative of the function f if you take the derivative and you get f. For all x in the domain of f, the process is called an antiderivative. The process of finding an antiderivative is antidifferentiation. Sophia, not right now. Alright, so can we actually find the antiderivative? Let me go to this slide. No, maybe I missed. Did I miss a slide? Where was... Oh, yeah, so this plus c that we have on here, that is every possibility, is what we need to write when we are finding all of the antiderivatives. So, when we go to this, I hope you're following me, I'm a bit distracted. When I'm trying to find the antiderivative, my capital F at x, I'm thinking, what function would give me 2x as an answer? But not just the 2x, but it could have any combination of numbers on the end. So we always put a plus c on the end to say that there could be another constant with that also. So just think of your reverse power rule here. If I got x, then I must have started with x squared. And if I had a 2 there, then I must have pulled a 2 out front. But there's already a 2 there, so we need to divide it by that 2. And I have my answer. But I'd probably write that like this, f at x equals x squared plus c. There's your antiderivative. So you're going to take what's here and divide it by your exponent. Let me show you how that works with this example. So to find capital F at x, put your plus c on there. It's easy to forget your plus c, so put that on there so you don't forget. Now, I have an x to the first, so I must have started with an x to the second. I'm going to take the number that's there and divide it by my 2. Simplify, and that's my antiderivative. So it would be, what's that, 2/3 x squared plus c. Your antiderivative. Working on this one, sometimes you have to be careful of just our specialty rules. If you try to start this one like this, x to the -1, when you add 1 to the exponent, you get 0. So that must have not been what it was. But then you think, oh yes, I remember that the antiderivative of 1 over x. I'll be done in a minute. Is the ln of x. So f of x equals ln of x plus c. Last one here, another one that is too hard to do just by normal antiderivative, but if you remember a rule that gave me that, you're thinking through that, and you remember inverse tangent of x plus c. Sophia, when I'm finished, I will talk to you. All right, let's keep moving. I need to get done. My kids are going stir crazy. Okay, so find the function with the given derivative whose graph passes through this particular point. So now instead of finding every general antiderivative with that plus c on the end, we need to figure out what that plus c actually is. And we figure that out by using this point. Our first step starts the same. So I'm going to rewrite this like this, negative x to the negative second. So as I'm finding the antiderivative, this time my antiderivative is just the function f. And so I would add 1 to the exponent, that'd be a negative 1. I'd take my negative here, divide it by my negative 1, and it just becomes positive. So that's my antiderivative plus c. So to actually figure out what c is, now we take this point 2, 1, and we substitute it in. So the y value is 1, the x value is 2, and I solve that for c. So 2 to the negative 1, that's 1/2. I subtract 1/2, and I get 1/2. So c equals 1/2. So my actual answer is this. F at x equals x to the negative 1 plus 1/2. Doing the same thing for this one. My antiderivative, add 1 to the exponent. Maybe now would be a good time to pause and try this yourself. Plus the antiderivative of 1. Plus the antiderivative of cosine. The derivative of sine is positive, so that means this negative must still be there, plus c. Substitute in your 0 for your x. Substitute in your 3 for your y. So 3 equals 0 squared plus 0 minus the sine of 0 plus c. 3 equals, let's see, sine of 0. Sine starts at 0. So this is just c equals 3. So my final answer, f of x equals x squared plus x minus sine of x plus 3. Alright, and the very final problem I'm going to do with you, are you guys hanging on okay? Is this one right here. So we want to find the velocity and the position if we know the acceleration. So you're thinking in your head, okay, acceleration, going up a step is velocity, going up a step is position. So, excuse me, I know here that the acceleration, a at t, equals 9.8. And I could put a plus c on there, but I know that at time 0 my acceleration is 0, so c is 0. To take the antiderivative of that, that would give me velocity. Well, so I need to add 1 to the exponent. Right now it doesn't have a variable on the exponent, so it must be 0. Add 1, you get 1. Plus c, but when time equals 0, my velocity equals 0. So that c is going to be 0. I'm just going to take it away. Find your antiderivative again. So antiderivative here. Now antiderivative takes me to my position function. Remember we usually call that s. And I need to add 1 to the exponent, which means I take my 9.8 and divide it by 2. I bring that exponent down to the denominator. Plus c. My c goes to 0 because the position is 0 when time equals 0 unless they tell us otherwise. So my final position function would be 4.9 t squared. To answer the question, here's your velocity function, and here is your position function. I hope you followed along. We'll talk about it on Monday. All right, bye-bye. You guys want to come say goodbye quick?
Bye.
Elijah, do you want to say goodbye?